Hello there, it's N8.1. This one is all about square root. Okay, so in order to do square root, you need to know a few things. You need to know what a whole number is. So those are your counting numbers. They are not fractions, they are not decimals. You need to know what a factor is. Well, the factors are the little guys that you multiply together to get the big multiples. So multiples are what you get when you multiply. You can draw a factor tree. So let's just do a real simple one over here. Let's do 20. So you put the multiple at the top of the tree, and then you break it down into its factors. And so it doesn't matter which factors you pick first. We could pick 4 and 5 if we wanted to. 5 is prime. It does not break down any further than that. It has no factors, except for 1 in itself, which wouldn't make sense to put in a factor tree, because then you would just keep on branching forever with your 5 and your 1. So once you get a prime number, you circle it and you're finished. 4 breaks down a little further into 2 times 2. And so if you wanted to write 20 as a product of primes, you could say 20 equals all those little prime numbers multiplied together, 5 times 2 times 2. So those are the factor trees. A complete set of factors for a number, that's a little bit different. I like to do that in an up and down chart. So if we were going to do, let's do 20 again. Okay, I would say do it like this, like a T-chart, and start with 1. 1 times what gives you 20? 20. Try the very next number. Does 2 work? Yes, it does. Does 3 work? Nope. How about 4? Yeah, because we just said that 4 times 5 is 20. How about 6? Nope. And actually, if you look at your bottom numbers, there are no numbers in between 4 and 5. So as soon as you can kind of close that loop, close the gap, you know that you are done. Okay, let's do a real quick one over here. Let's do 45. Okay, so 1 times 45. 45 is not even, so we can't use 2. 3 works. 4 doesn't work. 5 works. 6, nope. 7, no. 8, nope. And we've used all the numbers in between 5 and 9 so that we know we are done. Okay, back to our indicators. Perfect square, those are all those numbers that you can square root and you're going to get a whole number. So the square root of 25 is 5. So 25 is considered a perfect square. I know that squared and square root are opposite functions. So if you're doing 25, root 25 is 5. Going the other way, you would say 5 squared equals 25. Okay, so in one question, you're going to show the square root sign. And in one question, you're going to show the squared sign. And those are opposite functions, kind of like multiplying and dividing are opposite. I know how to use the square button on a calculator. Usually it looks like this. It's got an X and it's got a little 2 above it. I have memorized all of the perfect squares from 4 to 144. So that is 2 squared all the way to 12 squared. I know that perfect squares, such as 25 or 144 or whatever, can have a principal square root and a negative square root. So if we think about that, let's take the square root of 36. It actually could have 2 different answers, because if I square 6, I will get 36. But if I square negative 6, I will also get, those 2 numbers will both give me 36. So the square root of 36 could be positive 6 and it could be negative 6. I can find out if a number is a perfect square with and without a calculator. I can show a square root of any number on a number line using benchmarks. So we can kind of estimate where numbers will live, and I've got some examples of that coming up. using multiplying and dividing to estimate square roots. And I can retell a story about a historical math event. So I have a little info coming up about Archimedes or Archimedes. And let's get on to that one. So here is the list of numbers that you need to memorize. And I said you need to go up to 12 times 12. So it's handy to know all of those facts. Okay, it's just your times tables. Here are two examples of factor trees, which we've already talked about. So 400, they decided to break it down into 10 times 40. And 10 right away breaks down into two prime numbers, so we can circle them and we're done. 40, they decided to break down into 10 times 4. 10 breaks down into those two primes, and 4 is 2 times 2. So if you wanted to write 400 as a product of prime numbers, you could say 2 times 5 times 5 times 2 times 2 times 2. Or look at how many times we've used 2. 1, 2, 3, 4. Right? 2 to the 4th times 5 squared. You could write it as a product of exponents too. All right, here they've given an example with 72. 9 times 8, 9 broke down into 3 times 3, 8 breaks down into 2 times 2 times 2, and there is your factor tree. They could have done these in a different way. It doesn't matter what number you start with. If I want to break 72 down into, let's use 3 times 2 is 6, times 2 is 12, and then the other factors here are 3 times 2, which is 6. So 12 times 6 would give you 72, and then you could break the 12 down into 4 times 3, and the 4 breaks down into 2 times 2. The 6 breaks down into 2 times 3. Circle all my primes. And we end up with exactly the same set of prime numbers that we started with in the first example. So we have a 3 there, and a 3 there, a 3 there, and a 3 there, 2 there, 2 there, 2 there, and 2 there. So it doesn't matter how you start your factor tree, you'll end up with the same list of prime numbers at the end. Okay, estimating square roots. When you have perfect squares, such as 4, if you took the square root of it, it would give you a whole number. So in that case, it's 2. The square root of 9 is 3. So on the bottom, these are the whole numbers. Right? So we have 2, we have 3, 4 would be down there somewhere, down the road. Right in the middle of 2 and 3, let's put a little benchmark right there. We know that exactly halfway between 2 and 3 would be 2.5. And again, this is just an estimate. We're just eyeballing it. And exactly halfway here would be 2.25. And here, 2.75. Okay, and you could break it up further and say, well, that's 2.6, 2.7, 2.8, 2.9. I didn't do it very evenly. That might be important. Okay, so once you've got your benchmarks kind of laid out on your number line, I can say that 2 was the square root of 4, right? 3 is the square root of 9. So what would the square root of 7 be? If you said 2.6, that would be a very good guess. Okay. What would 2.25 squared be? If you said somewhere between 5 and 6, like about 5.2, that would be a good guess. So these number lines, you can line them all up and then draw out some benchmarks, which gives you a good way to estimate what goes on in between them. Here are some real life examples of where our First Nations artists have used squares and square roots. So a lot of detail, a lot of math went into these patterns. So you can see here, they've got the numbers here, 70, think it's 73 beads by 101 beads. So this was definitely thought out and planned before they started putting beads on this pattern. And you would have to know quite a bit about which numbers are compatible for square roots and how they all fit together in your pattern before you start. On to good old Archimedes. Archimedes, I think, is how we say it. So he's super old. He was born before Jesus, back in Italy. He eventually figured out pi, right? That 3.14, yada, 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 which is pretty amazing considering there was no such thing as calculus. The Greeks and Romans did not use decimals. They only used fractions because decimals just weren't invented yet, and they didn't have the number 0 at that time. So he was working with strictly fractions, and he was able to figure out this ratio that we use called pi. So he wrote a nice little book called Measurement of the Circle. Sounds riveting. I know, you just want to get out there and read it right now. But what he actually figured out was that if you're drawing a polygon, he started here, this is a pentagon, and then a hexagon, and then a decagon, etc., etc. The more sides he drew on his polygon, the closer his ratio was, the better his circle was. And so he ended up drawing a polygon that had 96 sides, and he used that for his calculations. So he got a pretty accurate version of pi that got him through, and the rest of society through, building whatever they needed to build that had circles involved. So he figured out that these two fractions, he knew it was somewhere between root 4 and root 7. And so he said 48, which is 3 times 4 squared, is about the same as 7 squared. By division, he knows that the root of 49 over the root of 4 is roughly 3. So very, very close to finding the square root of 3. And he called it 7 over 4. But then he did some later calculations and got even more accurate and figured out that it was somewhere between those two fractions. So, interesting dude. And that is your lesson on square roots.